Hi everyone, today we'll be talking about momentum in this video. So momentum is another term like velocity that often gets used in newspapers or magazines or on the news in very strange ways. We often talk about like a project gaining momentum, but what we mean by momentum is to do with mass and velocity. So when you multiply mass and velocity together, you get momentum. That's from a Latin word movementum, which means to move. So it's useful for describing the motion of an object. So momentum equals mass times velocity. It's a vector quantity, so it's the product of a scalar, mass, and a vector velocity. The direction of momentum is always the same as the direction of velocity. So if the mass is moving north, the momentum must also be moving north. It's not going any other direction. So that's important to remember. Okay, so our problem here that I'm going to work through with you is about a proton, which has a mass of 1.67 times 10 to the negative 27 kilograms. It's accelerated from 3 times 10 to the power of 4 meters per second north to 3 times 10 to the power of 5 meters per second north. So this is good. The direction of the velocity are in the same direction, so we don't have to do anything too complicated. We want to work out the change in velocity. In momentum. So just looking at the quantities, we've got this is our mass, this is our initial velocity, and this one is our final velocity. Okay. So what we can do, we can write down that the change in momentum equals the final momentum. We could call this PF minus the initial momentum. So just remember this triangle is delta. It's a Greek letter, capital delta, and it means change in, and you'll see that a lot in all sciences and maths and engineering. Okay, so we've got final momentum minus initial momentum, and these are vectors, and that's going to be equal to mass times the final velocity minus mass times the initial velocity. And I just put those little underlines, the lines underneath the vectors to indicate that they're vectors. Now you'll see various different notations as you go through physics for what a vector, how to denote a vector. So you might notice that we have a common factor here, m and m there. So we can take it out. We can write m v minus u. And then what we can just do, that's just a bit easier because you're taking away one of the multiplications, so you can just stick your mass, 1.67 times 10 to the negative 27, and that is times 3 times 10 to the power of 5 minus 3 times 10 to the power of 4. Now, units for momentum, you've got a mass here, so that's kilograms, and you've got the velocities here, which are meters per second. So momentum is always kilograms meters per second, that's the units. Okay, and when you throw that into your calculator, you'll get 4.5 times 10 to the negative 22 kilograms meters per second north, because the momentum is always in the direction of the velocity. Okay, so that's that question. Let's go on to the next slide. So the next slide, I've done a question here about impulse. So impulse is force times time. So it depends on the size of the force and for how long it is applied, and that's called impulse. It's also equal to the change in momentum. So I just write up the formulas here. So we've got F times t, sorry, that's F times t. Let's just rewrite that. Doesn't look particularly neat. Okay. So Ft equals mv, which is a vector, minus mu, and remember force is a vector, or Ft equals delta p, so change in momentum. The unit for impulse is Newton second. And I'll write that in there, so the units is Newton seconds, which is the same as, so it's equivalent to kilograms meters per second, which are the units for our momentum. So you can see that these match up. So you either see Newton second or kilogram meters per second. Okay, so our example is, for how long must a frictional force of 5.6 newtons act in order to bring to rest a mass of 2.4 kilograms moving at 6 meters per second north? So let's write down what we know. We know the frictional force, 5.6 newtons. We know that the final velocity must be 0 because we're bringing it to to rest, and the mass is 2.4, and the initial velocity is 6 meters per second north. So we've got our formula here. Get this thing to write again. Where's it gone? Okay, so we've got our formula. Now it's working again. Ft equals mv minus mu. Now we can rearrange this. We can take the t over to the other side. So we're going to move that. I'm going to get f. This is multiplication, so we need to divide 3 by t. You can do this first at the beginning when you have a formula to arrange it for the term that you want to solve. It is much better than putting the numbers in and then rearranging, because you're more inclined to make a mistake, which I just did, didn't I? Because I know the force. I actually want to put time on one side, so I'm going to take this one across there. So leave the time, that's what I want to find out, and put the force over there. Okay, so that was alright. So now we can put in, we can take out the common factor of mass there as well. So our mass is 2.4, our velocity 0 minus 6, and our force is 5.6. Now, you're probably looking at this and going, well, 0 minus 6 is going to give us a negative number, which it will. However, remember that impulse is a change in momentum. So if you look up here, it's a change in momentum. So it doesn't matter whether you get a negative or a positive at the end, because we're looking at time, and change is just a kind of an absolute value. It's just a change, right? Okay, so you will get minus 2.65 for your answer, but really that's because like the force is going to be acting in the negative direction as well, and we didn't put that in. So in fact we could put that in. That could be acting, because it's going to be acting in the opposite direction, the frictional force, to the direction of motion. So you put in the negative 5.6, which will turn this into a positive. That's probably a better way to think about it. So time is 2.65 seconds to bring the object to rest from 6 meters per second.